let's take a look at why benzene has some of its particular properties related to its molecular orbitals, just like we did with the conjugated compounds. Comparing benzene to just regular alkenes, we see some major differences here. Isolated alkenes, really even conjugated alkenes, will undergo addition reactions in which the double bond is removed. So just something simple like 2-butene, right, plus bromine, Br2, gives us 2,3-dibromobutane. We removed the double bond. It's an addition reaction. I completely added to that, to everything that was already existing in that compound. Okay? So sp2 carbons became sp3 carbons. That's a normal addition reaction. Benzene does something a little different. It does not undergo addition reaction. Okay? It instead reacts with compounds like bromine to give a substitution product. So let's look at this very carefully. Here's benzene. There's one H on each of the carbons. If I add bromine to it, we need a catalyst, but what we get is bromine that has replaced one of the hydrogens. To balance the equation, I need to have plus HBr. So big difference. An addition product would be addition of those bromines across one of those double bonds. So the removal of the double bond, I now have sp3 carbons with those hydrogens still attached. Here, I've removed a hydrogen and replaced it, substituted it with a bromine. So that's a key difference that aromatic compounds will undergo. That's chapter 16, electrophilic aromatic substitution, like that reaction right there. So let's look at this stability of benzene. It has a particular extra stability, even beyond just what we get from conjugation. So take a look. Here's cyclohexane, our baseline. Okay. Less stable is cyclohexene. Less stable yet, cyclohexadiene. That's 2 conjugated double bonds. We might expect benzene with 3 conjugated double bonds to be less stable yet, higher in energy yet, but it turns out that actual benzene is lower in energy than cyclohexadiene itself. Okay? So that means our aromaticity has gotten us 150 kilojoules per mole, for a fairly significant amount of stabilization. Significant amount of stabilization that is afforded by that benzene. This comes from heat of hydrogenation, right? Same thing we talked about with the alkenes, right? How much energy is released when we go from the double bond to a completely aliphatic saturated compound, right? Which is lower in energy. So let's look at benzene's structure. If we actually had single double bonds in the compound, we might expect them to be different lengths. Okay? Recall that double bonds are quite a bit shorter than single bonds. Experimentally, we see the actual structure has all 6 carbon-carbon bonds equivalent. We can think of that a couple ways. There are 2 equivalent resonance structures that add together to make the molecule. Okay? So 3 of them have double bonds in one resonance structure, and the other 3 have double bonds. So if I look at any one bond, we have a bond order of 1.5. Right? Remember, a single bond is 1, a double bond is 2. So each of those carbon-carbon bonds is equivalent to somewhere halfway between a single bond and a double bond. And the actual structure, the electrostatic potential map here, shows electrons evenly distributed symmetrically around that ring. We're not alternating single and double like that. That's why sometimes that benzene is drawn as a circle, right? That extra bond is drawn as a circle inside of that hexagon. But in this course, we're pretty much always going to draw just one of the resonance structures, because that much more clearly shows the number of pi electrons, and when we're doing actual reactions with those pi electrons, we can follow them much more easily. So just pick one of the resonance structures and draw it that way. The carbons, of course, are sp2 hybridized, which makes benzene planar. If I draw it sort of from the side, like that, if it's sp2 hybridized, that means there are p orbitals that are perpendicular to the molecule. Okay, so we'll draw those going up and down. That means there are hydrogens sticking, right? There's one hydrogen in each case sticking directly out from the carbon. Okay. So the sigma bonds are what's going around there. The pi bonds come from overlap of those p orbitals, right? So the consistent overlap of the orbitals all the way around the molecule, like that, is what makes the structure the way that it is. So benzene, perfectly flat, like that. P orbitals, perpendicular to the plane of the molecule, going above and below it that way. So just like when we had the conjugated dienes or polyenes in the last chapter, we can envision the interaction of those pi electrons in terms of molecular orbitals. So we had 6 p orbitals. I drew them in that last picture. Those will combine to form 6 molecular orbitals, just like we've done before. The difference here, when I have the orbitals in a ring, in an uninterrupted ring like this, is that after the lowest energy molecular orbital, they'll go up in pairs. So I have one lowest energy molecular orbital, just like always, where it's all bonding. Right? This one is all bonding. So I have one color lobe all the way across on top, the other all the way across on the bottom. So they're all completely overlapping. Go one energy level up, and now I have 2 equal or degenerate molecular orbitals that now contain one node. And the reason we have 2 of them is because there's 2 ways to do it. That one node can be going through a CC bond, right through the middle of the molecule. So 3 up on one side, 3 down on the other side, of talking about the phases of those orbitals. Or a node can go directly through 2 opposite carbons. So I have 2 up on one side and 2 down on the other side. Both of those have essentially the same amount of bonding compared to antibonding. So they're equal in energy. The ones after that, which have 2 nodes, right? One going through the carbons, one going through the bonds, and vice versa. You can look at those that way. And then we only have one left, so that goes on top. So this is one manifestation of what's called the polygon rule, where the molecular orbital diagram of an aromatic system resembles the polygon itself. So if I have a 6-membered ring, I will have 6 molecular orbitals that sort of are arranged in this diagram like a hexagon would be. But the one thing you have to remember is that you have to point the vertex down. So no matter what size ring you have, whether it's 3, 4, 5, 6, 7, always start with 1 on the bottom. Right, there's my polygon. So here's 1 on the bottom, then 2 degenerate after that, 2 degenerate after that, then 1 that's up on the top. And as always with these sort of things, the lowest one will be all bonding, the highest one will be all anti-bonding. So there's nodes between each of those p orbitals. In the case of benzene, those 6 pi electrons that we talked about, where each of the carbons contributed 1 of its extra electrons, those 6 pi electrons can be shown occupying the 3 bonding orbitals. So remember how we do that. Up, down in the bottom, up in one, up in the other of the degenerate ones, just like molecular orbital diagrams or any kind of electron diagrams we put for equivalent energy orbitals. We put them single first before we pair them up. Okay? So we go up, down, then down. These have all been completely occupied. All the electrons are paired. Okay? That's what gives benzene its extra stability. It has 3 occupied bonding orbitals where all the electrons are paired. That's a especially stable electron type configuration.